Good.
Yeah, like two big things.
So, yeah, new unit. So this is sort of a one lecture unit, sort of two lectures. So this is a reminder. I'm going to talk about this today. Then on Tuesday, we'll have kind of an open lab where we can work on your final projects. And so if you'd like, you can come here. I'll be here. Maybe Eric will be here, and then we can work through any problems you're having or anything sort of last minute issues you might have. So you have plenty of time to get those fixed before the final project is due. And then a week from today, Thursday, Eric will be giving a lecture related to his research involving kind of sustainable irrigation practices or lack of sustainability and questions relating to unique problems to Phoenix and irrigation and flood irrigation and things like that, and how these quantitative methods can relate to that. Then in the next week, that Tuesday, which is the last week of classes, we'll have a review session. So just kind of similar to the midterm review session. Your final projects and presentations will be due Wednesday night. Thursday will be stage one of the midterm exam, or sorry, the final exam. So we'll do, same sort of thing where I'll open it up Thursday and give you Thursday, Friday, Saturday. And then stage two, technically, you can come to class during finals week during the window, which I think is available on Canvas. I'll have to look it up and I can post an announcement. I think it's one of the 9 o'clock windows, like the 9:30 window or something like that. Again, I'll have to look it up, but I've posted on Canvas. And you can come here to do your stage two, the collaborative, but you don't have to. But you'll have, I think, Monday, Tuesday, and Wednesday to knock out your stage two. So it's very similar to the midterm setup. So that's kind of the schedule going forward. So before we start into today, are there any questions about the timeline moving forward? All right, great. Questions online? I notice online that the camera seems to be doing that flickering thing. I apologize for that. And whenever I am about to report that that's occurring, it stops occurring. So, maybe I'll give it another shot. Okay, so yes, today we're talking about randomness and chaos. These are two terms that are related to the predictability of systems, and they're often associated together, but they're distinct. They have almost nothing to do with each other. So you should never use them as synonyms. And so we're going to talk about that today. So on one side, we have randomness. And randomness is actually a modeling tool that simplifies model building. And we'll talk about what that means there, but kind of to give an idea of where we're going with that, very few processes in nature are actually random. I mean, you have to get down to like the quantum mechanical level where you actually find true randomness. Most of the time, they're just complicated, involving too many variables for you to really account for. And whenever you leave out some variables, there is some non-determinism left over. And we can, rather than trying to incorporate every variable possible, we can instead say, these are the only variables that really matter, plus randomness. And that's what we're kind of talking about here, where we actually simplify models by putting in randomness, because it allows us to not have to model everything. On the flip side of that, chaos is an apparent randomness that emerges even from simple systems that are not random. So sometimes you can build a system that only has 1 or 2 stocks, and you run it, and we're going to see here, it's an extreme sensitivity to initial conditions. If you initialize it with your stocks being at one level, you get one output. If you slightly change that level, you get a very different output. And so that's what chaos is. It gives the appearance of randomness when in reality, everything is actually 100% predictable within the system. And so when we're looking at data from real world, if there are patterns we don't quite understand, we have to ask ourselves, do we need more variables to understand these patterns? Or are these patterns actually completely understandable from the few variables we have? They're just related in a very kind of non-trivial way. That's what we'll get into here. So that's kind of what we're talking about. The difference between randomness, which makes modeling easier, and chaos, which makes modeling harder. All right, so let's start with randomness. So randomness is also related, there's other words, stochastic. And again, a lot of people, before they take a modeling course, maybe even some after, treat these as synonyms, stochastic and random. They're not really synonyms, they're very kind of different words. And so this term stochastic is a modeling process where you build models that use randomness instead of deterministic rules. So it's kind of like I said before, instead of incorporating every single variable that you might think that matters, you incorporate only the ones that matter the most, and then the rest that collectively create deviations from what you'd expect from the ones you picked. Instead of modeling all of their effects, you just bundle them together and say, plus randomness. It's just a little bit extra randomness. And so it's this approach of modeling something as if it's random, even when it's not random, is what we refer to as stochastic model. So the word stochastic actually it comes from a Greek term for guessing or conjecturing. It doesn't even have anything to do with randomness. So initially, the first people that used stochastic modeling wanted to have a name for it. And they were afraid that when they published models that had randomness in it, that people would read those and say, wait, you're modeling a system that's not random. Why are you putting randomness in it? And they said, well, we're going to make the guess or the conjecture that this system is random. Even if we know it's not random, we're going to say we can build a good enough model where the system is random. So the real system is not random. If you knew everything about the world, you could come up with a rule that would predict what's going to happen the next time step. So if I know where every student is on the university and how hungry they are and all these different details, I could predict what happens next at the Memorial Union's food court. But in reality, I can't know every single student on the university and how hungry they are and everything like that. So I model how many people show up at a restaurant in the food court randomly, as if it was just drawn randomly from a distribution, as if there was no deterministic reason for it to be there. And so, so that's replacing a fine-grained understanding of a system with a guess that the behavior is fundamentally random without caring about whether it actually is. It's you end up getting the same sort of model without having to add all the details. And as a consequence, it reduces your burden for boundary accuracy and structural accuracy. Remember, though we introduced those terms last time, boundary accuracy basically is what variables you included. Structural accuracy is all of the relationships between those variables. And so the idea here is that rather than trying to include every single variable under the sun and every single relationship among those variables, we say, you know, we'll only include the really important ones, and the rest we'll just sort of try to model as if there was a random noise that was driving the rest of our system. And I'll give an example of that here in a second. So big thing here, if you've heard these words stochastic and random, don't use them as synonyms, they're different. If you've heard the words chaos and randomness, also different words, they're not synonyms. So what's an example of this? Well, we've seen this back from lectures D1 and D2, bacterial modeling process here. We're saying modeling the reproduction of bacteria. And we said, you know, on average, every W time units, it's like a waiting time, one bacteria turns into two. And so if we were to look at sort of a real trace of the system and count how many bacteria there were, then we'd have a certain bacteria at some time point, and then some duration after that, less than the average waiting time, one bacteria would turn into two. Maybe after another duration, you get another reproduction event. Maybe another duration that's larger than average, you get another reproduction event, and so on. There's a lot of variability here where the distance between the reproduction events isn't always exactly W. Sometimes it's less than W, sometimes it's more than W. And so we took the approach of saying, well, let's model the average behavior. So we said, we're going to take this, this description of this event-based system where events happen kind of randomly, or yeah, I'll say happen with variation. And we're going to replace it with a system where everything's kind of operating in the average case. And so we're going to say, well, if I were to have a time period with one bacteria, then I'd say on average, what's the rate of generation of new bacteria in that constant time period? And that gives me kind of this interest rate idea here. I've got kind of a bank balance and a generated interest. And so over that one time period, this is like the average amount of money in the bank. And then I generate over the next time period, the average amount of money in the bank afterwards, and so on and so forth. And so we're capturing the average behavior of what's going on with these bacteria. So that's what we mean by flows. A stock and flow model typically is modeling the average. So every individual trace of a real system is going to vary from that average. But the systems, if we look at a lot of systems, a lot of Petri dishes, if you averaged across the Petri dishes, that average would look like your stock and flow model. So the question here is, all right, so this is great, that's the average. What if we really wanted to know the true variation? So the idea here is this is in real systems, then sometimes you wait a lot longer for a reproduction event. Sometimes it's a lot shorter. So if in the restaurant case, for example, it might be that on average you get 5 people per hour, but there might be some hours where actually nobody arrives, and some hours where you get 20 people. And maybe over the day it was 5 per hour, but it might be important to know that some hours of the day you're going to get 20 people arriving, because then you're going to need to staff those hours. So you're going to need to know the real variation. Knowing the average behavior of the whole day is only like, it's useful for thinking about your business in the long run, but for managing it in the short run, you really need to know at 1 o'clock, what am I going to get? At 2 o'clock, what am I going to get? And so on and so forth. So we might actually care about the real variation. So the question is, how do we build a system that models this variation? Now, when the approach we've taken in this class, this endogenous approach, is that we grab as many variables that think that are possible or that we need, and then we use those to generate these simulation models. Now, if I really want to know in a bacteria case why some bacteria takes longer than W to reproduce and other bacteria are shorter than W, I have to ask myself about the cell physiology of what goes on in a little bacterium cell. There's probably a lot of crap I need to know in order to really predict that. I need to know where all the organelles are, how much ATP is in the cell. There's all of this different stuff that in order to predict this variation. And so if I'm simulating a petri dish of 1,000 cells, 1,000,000 cells, each individual cell is going to have its own little packet of information about its little local state. That's like a lot of information that I'm going to have to put on this ugly model. It's just too much. The model would end up being way too big, too hard to get right, because all of those parameters, you're going to have to find data to fit those, and it's just not going to work. It's not practical. So to get the boundary, to take this purely endogenous perspective where everything's inside the model, we'd have to put too much in the model for it to really be practical from a modeling problem. So we're not going to take that approach. Instead, what we're going to say is, I only know a little bit. I know how many bacteria are currently alive. And then I'm just going to roll a die. I'm going to say that I know how many bacteria are alive now. And all I really need to know is what is the duration between whatever the state is now and the next reproduction event. And that duration, I could try to look at all of these variables, but in reality, why don't I just roll a die? And if it comes up 6, I'm going to use one duration that's less than W. If it comes up 2, I'll use a different duration that's less than W. If it comes up 6 on its side, I'll use a different duration that's more than W. It comes up whatever that number is, it's kind of blurry now, but you get the idea, is that every side of the die, and maybe how that die is oriented where it falls, could represent a different duration that I'm simulating in between reproduction events. And if I kind of set up the table of the mapping between die rolls and durations, I probably can get something that looks pretty darn realistic. So that's kind of the idea there, is that the outcome is not going to look that much different if I use die rolls to determine these durations versus a truly endogenous perspective where I got to know all of these details. I can throw out all those details, just say, all I know is how many bacteria are here, and I'm going to roll a die to figure out these things. And this is the same thing you do in board games, right? Like, if you're playing some game where now you have to fight a dragon or whatever, you don't know exactly how that's going to go down, right? I mean, there's, and it's going to be stochastic, right? Sometimes you beat the dragon, sometimes the dragon beats you. It's just like life. And so rather than trying to figure out a deterministic rule for, based on, like, you could come up with a rule at the board game. You could say, if you're wearing black and you're, greater than 5'10" and all of these different things, then you always beat the dragon. And but then you can say, well, why does that rule make the most sense? So then it opens things up to question. And you can say, okay, fine. actually what we're going to say is this dragon is a pretty formidable beast. You have a certain weaponry. Based on the weaponry you've accumulated and how formidable the dragon is, we're going to roll a die. And if that die is greater than five or greater, it's 5 or 6, you beat it. Otherwise, you lose. And we've now gotten rid of all of the details of exactly what happened during that fight. We've just replaced it with a random distribution. In reality, whatever that means, when the case comes to a dragon, a lot of other stuff happened to get you to the point of beating that dragon. We don't care though. We just assume that it's totally random whether you beat the dragon or not, but we adjust the distribution of outcomes based on a few properties that we do know. And we end up getting a result that looks pretty much like real data, whatever real data would be for a dragon. Same idea here. And so that's what we mean by stochastic modeling. Stochastic describes a model, not a phenomenon. It is an approach of building a model of reality that substitutes randomness in place of a lot of details that would be really hard to figure out and put into your model. So it accounts for omitted degrees of freedom. So instead of having 1,000 parameters you have to nail down before you can hit run, you only have 3 parameters to nail down. You maybe have to know, how many hit points, whatever the dragon is, what your weaponry is, and some distributional parameters about that die roll. And as long as you have all 3 of those things, you can proceed without any of the other details. That's stochastic modeling. That's what is going on here. It actually makes modeling simpler. Adding randomness makes models simpler. The same way adding randomness makes game playing simpler. Okay. So, this is kind of my die roll example here. So if you have a 20-sided die, that gives you a lot more flexibility to set up these random outcomes. Because now you can say, I've got sort of a bunch of different ways I could combine these 20 outcomes to give me a smaller set of outcomes. So I can simulate a 6-sided die with a 20-sided die. So, and I could say that I want to make a weighted die. Like instead of a fair 6-sided die, how do I make an unfair 6-sided die? Well, if I have a 20-sided die, I can say that if you roll a 1 through 10, that's equivalent to a 1 coming up on the 6-sided die. But if you roll any of these, like 11 or 12, you get a 2, 13 or 14, you get a 3. And so you're going to get 50% of the time, you'll get a 1, and then 12.5% of the time, you'll get each of these other numbers. Or maybe I didn't do that right. Or 10% of the time, you'll get each of these other numbers. So 10, 20, 30, 40, 50, 100. So this is a way that if I have a die that has more sides than the die that I'm using, I then now have the ability to create these rule cards that reshape the random outcomes to make it more realistic. And this is the reason why in a lot of board games, you're not given 6-sided dice, you're given 20-sided die, because that gives the board game designers the ability to more flexibility to come up with random outcomes. And it'll turn out that we do the same thing in our simulation models. Every computer, no computer is random. But as I'll show you, every computer has their equivalent of a very, very, very many-sided die that's inside them. And it happens to have the property that that die roll always has the same pattern of numbers every time you roll it. But you can choose which die you're going to work with at the time, and it'll look pretty random. And because there's so many sides of the die inside the computer, then you can create a bunch of modeling rules to generate random outcomes that look like the actual statistics of your real system. So as an example of that, if I wanted to do like simulate a weighted coin, so it's just got 2 outcomes, heads or tails, but I want to make it heads very often and tails not that often, then I can say, if you get 1 through 15, it's heads. If you get 16 through 20, it's tails. And so that's a way that without having a coin inside the computer, I can simulate a coin that's unfair. And this represents like, let's say you wanted to beat the dragon, only 5 out of, or how many times does the dragon beat you? Well, we'll say that this way, if heads is when the dragon beats you, then it beats you 15 out of 20 times, and you only beat it 5 out of 20 times. So that's a way of us encoding these 2 outcomes, win or lose. Or in the case of bacteria, maybe birth or death. So that's kind of what we're moving towards here. And so inside this computer, I've mentioned that like in every computer, there are these things called random number streams. And they're just mathematical formulas. So there's a formula for stream 0, a formula for stream 1, 2, 3, or whatever. And when you run a simulation, you can tell a computer which stream to use for that simulation. And the idea here is I could say, I'm going to run the exact same simulation. Well, I'll run the simulation using random stream 0. And I'll get a certain outcome, and it'll have variability in its output. If I were to rerun it, it'll be the exact same outcome with it'll have variability in time, but it'll be the same pattern. So then I can tell the computer, this time run the simulation with random stream 1 instead of random stream 0. And then it'll generate a new variable outcomes that will be different than random stream 0. So the idea here is if I want to simulate 5 petri dishes of bacteria, I have the exact same model of a petri dish, but I run my simulation 5 times. Once with random stream 0, once with 1, once with 2, once with 3, once with 4, once with 5. And that will give me 5 different traces, 5 different behaviors over time that sometimes bacteria will be reproducing sooner, sometimes later. And if I look at all 5 of them, none of them will be equal, but they'll all kind of be close to that trend, which is the general stock and flow diagram that we built earlier in the semester. I'll show you an output from that. So in order for our sims to have different outcomes, we use different random number streams, but each random number stream doesn't actually produce random numbers. It just produces a pattern of numbers that's not very predictable, that is approximately random. But if you rerun the sim with the same stream, you're going to get the same outputs of that sim every time, which is why we end up running the sims with multiple random number streams. And that's like, again, having different petri dishes on your table, so that if you get an outcome for this one that looks really interesting, you want to make sure that it's generalizable and not just a lucky case. So if you get that same outcome when you try random number 1, random number stream 2, et cetera, the same outcome across all 5 streams, you've probably uncovered an interesting property that's general to the system. If that property only shows up for one of these random number streams, it's just a lucky outcome, you know? So like if you designed a restaurant model simulator and you'd get really high profits from whatever organizational scheme you implemented in your restaurant for this random number stream, you then say, well, this is like one set of customers. And I might've just gotten lucky with my customer set that day. So this is like a different set of customers, a different set of customers, a different set of customers. So by running the computer model with different sets of customers, if I get really high profits in all 5 cases, then that means I've probably come up with a good way to run my restaurant. But if I only get really high profits in one of these cases, it was just good luck. And the other cases kind of show that, that I can't count on just that one result there. So that's how we make use of pseudo-random numbers in these systems. So let me show you an example of that, and then I can ask for some questions here. So this is our traditional model of bacteria. I got rid of the births. So we just start with a population of bacteria, and we allow them to die naturally. So I've got the average lifetime of the bacteria here. We call it L for short. The population here, we could call it P for short, and then an outflow deaths B. So anybody have a guess for what formula would I put inside here, this deaths outflow? You've gotten some practice at this. So if this is L lifetime and this is P population, then how would I combine P and L inside this flow to get, yeah. Exactly. So the answer there was, would you do deterministic population divided by average lifetime? And that's exactly what I would do here to get the average behavior over time. So if I did that, then I could start out with 1,000 bacteria in my initial population. I could hit play in VinSim, and it would start with 1,000. Because there's no births, the bacteria just dying, you would get this smooth decay, where eventually it would kind of asymptote out at 0. So this is just the bacteria dying off with an average lifetime of this lifetime. So there's no variation there. This is just on average how the population would act. If I looked across my 5 petri dishes and took the average at every time instant, then this describes the average that I'm going to get across those dishes. So how do I simulate an individual dish? So to get the variability, I'm going to modify it slightly. And so I'm going to create this outflow called stochastic deaths or whatever. Of course, you wouldn't call them this in reality. I'm just naming them these awful names just to emphasize what we're doing here. But you would still call it deaths in population. But I put a different formula inside here. Now, things I want to point out in here, it looks, so what we're trying to do here is rather than thinking about the average number of bacteria, we actually think about the actual number of bacteria in a run. And so we could say at the current time, there are 10 bacteria. And so the question is, as I move to the next DT time step, how many bacteria die? That's kind of the question there. So which of these bacteria will survive as I move to the next DT, the next time step? And so imagine I flipped a coin for each one. This is kind of like gladiator sort of thing. Like, it's a thumbs up, thumbs down sort of idea here. And so we give a thumbs up and thumbs down to each one of these bacteria based on the general probability that any bacteria will die. And so if we did that correctly, then we're going to see that so many of these bacteria survive and a certain fraction of them die off. And we're just going to subtract from the population the number that die. And notice that there's no real numbers here. It's all whole numbers. Like, so you started with 10 and you're going to subtract off 4, and then you're going to get exactly 6. There's no 6.6 bacteria anymore. We're actually simulating what would be a real trajectory of these bacteria. So we subtract those 4 out and we're left with these here. So then the question is, no fractions, like I was just saying there. So how do we actually implement that in VinSim? Well, there is, this is kind of a mouthful here, but the syntax doesn't matter that much. I'll show you kind of the salient features here, but there is basically this function here called random binomial. This is basically a way to simulate a bunch of coin flips. So as we'll see here in a second, so don't be distracted by the ugliness of this right now. Be distracted by the ugliness right here. The idea here is that this is going to say, if you flipped a coin 10 times and that coin had a certain probability of being heads, how many heads would come out of that? That's what random binomial is going to give you. And it's going to be a random number. If you call it over and over again, sometimes it'll be 3, sometimes it'll be 2, but it's consistent with that experiment. You take a weighted coin, you flip it 10 times, you count. Then you put that away, take another weighted coin, you flip it 10 times, you count. That's what this is doing right here. And so it takes a random stream on the input and it outputs a number. And so if I put a different random stream in here, I'll get a different set of numbers on the output. If I always keep the same random stream and I run my simulation over and over again, I'll get the same every DT. Like some DTs will be 3, the next DT will be 4, the next DT will be 1. If I were to stop my simulation and rerun it, it'll be that 3, 4, 1 pattern over and over and over again. Unless I stop my simulation, change the random number stream, then I might get 2, 6, 1. And then, but if I reran it without changing the stream, it'll get me 2, 6, 1 every DT. So it allows variability across time steps, but not across simulations unless you change this random number stream. And we'll see that when I give this kind of example here. So yeah, so the kind of this ugliness here in VinSim, and this random binomial is the count of death events during a particular time step. And so how does that work here? Well, this parameter back here, you're telling VinSim which random number sequence to use. So you can, this we'll see, it'll just be like a number that you pass in. Say, VinSim, go use that die, or go use that die, or go use that die. These things here are more advanced things that we don't worry about. So we just set them to 0 and 1 for the purpose of this class and pretend that they don't exist. This parameter here is the number of coin tosses, which in our case will be the number of bacteria. So for every bacteria, you do the gladiator thing and you say, do you survive or not? Where your thumbs up has the probability of survival and the thumbs down is the probability of death, 1 minus the probability of survival. So then you have to specify that probability. So in the coin example, it's probability of heads. In our example, it'll be the probability of death. And so in our case, the probability of death is going to be time step divided by average lifetime. Now, where does that come from? Well, if you think about it, if every bacteria lives for this long, this average duration, and I'm only simulating a tiny little time step, then what I'm saying is that if I'm simulating 10% of the average lifetime, then there's a 10% chance that this bacteria will die. If I'm simulating 100% of the average lifetime, then there's a 100% chance that this bacteria will die. So the shorter you simulate, the less of a probability you're going to catch death in the act. So that's where this comes from. It's the dt divided by the average time between events. And then finally, if for this output, it's the minimum value that this thing can give us and the maximum value. And in our case, we want the minimum value to be 0. So the smallest thing can happen is nobody dies. The maximum value is going to be the number of bacteria. So in any one time step, no more than the number of bacteria can die. So I put all that together, and I get this thing that I could implement inside this Vinsim formula right here for the flow. And so it's just, again, it's the minimum number that could die, 0, the maximum number that could be die, the population size, the probability of any one death, which is just dt divided by the average lifetime. Then again, it's the number of flips I have, and that's just, again, the population size. And then some details of the implementation here, where the random stream is the only thing that we really care about here. There's 0 and 1, just ignore them because they're kind of for advanced use. If I do that and simulate, so I did this in Vinsim, and I've got my deterministic formula, that's the blue line, the smooth line here. If I simulate instead this one, this is the red line, which I'll zoom in on here in a second, it follows close to the blue line. But if you look closely, you see the red line kind of comes off it. If I zoom in a little bit, like here, then this blue line is a nice continuous, what happens in the average case. But this red line, notice that it goes in steps. So this actually is going to be purely whole numbers. So some time steps, no bacteria die, and the population stays constant. Some time steps, maybe only one bacteria will die. And so because our time steps are so small, it's very unlikely that more than one bacteria will die at a time. But you'll get sort of the death rate, or the average lifetime is going to sort of affect how large these plateaus are. So how long you wait until you get one death. And so you end up getting this thing that, again, roughly follows close to the average, but it actually has the real variation that you might see in a single Petri dish. And I can take that and I can say, well, I'm going to generate, see, I put this random stream as a variable coming in here. So I had Vinsim simulate this a couple of times using a different random stream for every simulation. So this is random stream 0 is the red line, random stream 1 is the green line, whatever that line is, the kind of purplish line, and the darker purplish line 2 and 3. And as you can see here, I've plotted all of those things plus the average on here, and you start seeing that these lines really are fuzzy around the average. And if I zoom in on them, then I can see that all of them stick close to the average, but they each are unique. So it's like Petri dish 1, 2, 3, and 4. At any one time, like time 35, if I was to go to time 35 and look up, then Petri dish 1 tends to have more bacteria in it than 2, than 3, than 4. If I were to average across these, the average across those 4 Petri dishes would be roughly where our deterministic model would be. And so this gives us our variation that's consistent with our deterministic model, but it's sort of more realistic. This is kind of the cool output here. So it captures this realistic variability, which is good. So the upside is more realistic. The downside is, if I didn't simulate this average model, if I wanted to know, well, what is the average model, I'd have to simulate a lot of I'd have to put in a bunch of different random number streams in order for me to sort of start, like if I didn't have this blue line to begin with, if I only simulated one random number stream, I wouldn't be able to know what the average behavior was. If I simulated 2, I might get this one down here, or I might get this one up here. If you average these 2 top ones together, that's not the average behavior. So in order for me to capture the average behavior, if I only have the stochastic simulation, I need to generate lots of different outputs. And that's exactly why in real experiments, in real laboratories, they have to replicate. They can't just run one Petri dish, because you might get lucky. And that's what the top one is. The top one is a Petri dish with a relatively low death rate just by chance. The bottom one is a petri dish with a relatively high death rate just by chance. The average death rate, which is more generalizable across petri dishes outside of the lab, is the blue one. So in order for me to know on average what's going to happen, then I need to have lots of different petri dishes, and that's equivalent to having lots of different random number streams. All right, so any questions about this output, this general approach here? It's a very different way of formulating these expressions, but the logic is very similar to what we've been doing. We're now just simulating real traces and not average traces. Okay. Questions online? Okay. Now, I've mentioned this for just a bacterial example. How do you generalize this? Well, it turns out that if you have any deterministic flow model, like you've been building in this class, there's a way to modify your flow expressions a little bit to get the variability out. And that's what I've got presented here. So, if you have something that is a deterministic inflow or outflow, it's got a flow rate that's inside here. We have a way to convert any flow rate into this stochastic behavior inside VinSim. And the basic idea here is that we need to figure out the probability of a single event, in this case, a single death, in a time step. And if we have a model for that, then we can generate this stochastic outflow. And it turns out that this rule, if your dt is really small, it's got to be sufficiently small. We already want small time steps, but so if it's really small, then it turns out that whatever flow rate you have, if you multiply that flow rate by your dt, by your time step, the number you get will be less than 1 because your time step's super small, and the number you get will be a probability of an event occurring, either an inflow event or an outflow event, in that little time step. So that ends up being our model that allows us to turn any flow rate into this probability. Once we have that, we can go into Insight Maker, and it's got these little things like this little if then else here. So what this VinSim expression says is basically this flow rate fits into here, and it sets up a probability, and VinSim will generate a random number between 0 and 1 that's a uniformly distributed between 0 and 1, and it will compare that uniformly distributed number to the probability that we calculate, this time step times flow rate. And that basically will, this expression here, if the random number is less than or equal to this probability, that will be true this probability amount of time. So by doing this, this allows me to say, was there an inflow event or an outflow event in this time step? And this probabilistically will sometimes come up yes, and sometimes come up no. If it comes up yes, I return a 1, saying there was that in this time step. If it comes up no, I return a 0. So that's kind of the logic behind here. And none of that, you don't need to necessarily know all of those details, but what I'm trying to show here is that even if you didn't know everything that was going on here, you could take any of your existing models and you just have to draw a random stream going into a random stream input. This is a constant that you can put a 0, 1, 2, whatever into it, and draw that going into your flow, and then go into your flow and then copy the rate expression that you already have and put it off on the side, and then paste in this expression down here. But then instead of flow rate, put parentheses and then paste the original flow rate into here. And if you do that and hit go, then you'll end up getting a stochastic output where you get variability that will be consistent with your average model you had before. So this is a way to turn any deterministic model into a stochastic model that has variability, but whose averages, whose statistics are consistent with your original deterministic model. So that's kind of how to do that. So I'm not going to quiz you on this expression, but I just want you to know that in principle, you can convert all of the models we've talked about this semester into stochastic models with a simple formula like this, so long as your time step is super small. All right, so any questions about this approach before we turn to chaos? well, hopefully we won't descend into chaos in the class, but you know what I mean. Gesundheit. Okay. The big things I want you to take away from this, I'm not expecting you to do, I mean, if you want to do some random, use some randomness in your models or some stochastic modeling in your final projects, fine. I'm not asking for that necessarily, but I do want you to be familiar with this idea of stochastic modeling, of using randomness to make things simpler. Those are sorts of things I may ask you conceptual questions about, say, on your final exam. Okay. All right. Actually, let's do an attendance question. So I'll bring up in the chat here the attendance question link. And the question here is, stochastic comes from the Greek for what? And I mentioned there's two things. So stochastic comes from the Greek for sort of two words. And you can mention either one of those is what I'm looking for that. So a lot of people think stochastic has something to do with randomness, but the word stochastic does not come from the Greek for randomness. It comes from the Greek for something or something else. And you can give me either one of those. Again, I don't grade these for correctness, just for kind of coherence. So try to remember what I said. Stochastic, what is stochastic? It's sort of a stance as opposed to, it has nothing to do with randomness. So stochastic comes from the Greek for one of these things. Any guesses? Anybody? That was a hint. Yeah. To guess or conjecture, that's what I'm looking for here. So stochastic is basically Greek for guess or conjecture. Okay. So, so the other thing we want to talk about here is chaos. A lot of people will say, I looked at a data set or whatever, and I couldn't make sense of it. It was just chaos or whatever. And they'll, in their heads, I think they're thinking randomness and chaos are the same thing. But to modelers, they're distinct, and the distinction is important. So chaos is an extreme sensitivity to initial conditions. Almost all the models we've looked at so far have not been chaotic. So we've looked at models like this. So like this fish stock here. So I'm not going to show you the net regeneration curve or whatever. We should all sort of be familiar with this basic idea by now. But the point here is if I run this in Vensim, I can choose different initial conditions for my fish stock. I can say I initially have 1 fish, 5 fish, 10 fish, 100 fish, whatever. So I have different initial conditions that I can start this simulation out. If I hit play for these different initial conditions, things start out differently in the trace, in the behavior over time, but they all end up in the same place. They all end up at carrying capacity. So we say that this system is attracted to this output, this steady state outcome. We'd call this sort of a stable equilibrium of the system, and there would be a single stable equilibrium of the system. Well, in this one, extinction is another one. But the point is that once things get sufficiently close to this point here, you kind of can't tell what initial condition they came from. Like eventually they all get buried up here in the steady state outcome. And I can't really tell if it reached carrying capacity from an initial condition of 10 versus 100 or whatever. So regardless of your initial condition, the outcome at steady state is the same. That's the almost all of the systems, I think all of the systems we've looked at this semester have had this property. It didn't really, if you had a major change in initial condition, like if I make the initial fish density 0, it ain't gonna grow, it's gonna stay 0. But if I make it 1 or 100 or whatever, it's really robust to initial condition. It always ends up at carrying capacity. This is not a chaotic system. So a chaotic system would be one like this one. So this is and this is just an abstract model, but you could imagine building models that have this same property. And this is called the Mackey-Glass system. In the Mackey-Glass system, you have a single stock, and it has an outflow and an inflow, kind of similar to the fish dynamics here. But we model the outflow and inflow with this formula down here. So it looks a little ugly, but these are just variables in the model where X is the stock. And then we've got these parameters, beta, which is just a constant you would put in your formulas. N is a constant you put in your formulas. Gamma is a constant you put in your formulas. This thing over here is the outflow. This over here is the inflow. So I could put this fraction with the beta up here in this formula, and I could put this product here with gamma times x in that formula, and I could simulate this in VinSim. The one important thing here is that this variable here is a delayed version. It's a fixed delay. So this variable that goes here, which is in the numerator and denominator of this inflow, is a fixed delay version of x. So I put like fixed delay x comma tau, whatever that tau is, 5. So I could choose numbers here. So these are special numbers I've chosen over here, and I'll put those in. And you can simulate this in VinSim. You can put this, you can say this is a 2-second delayed version of x. You can put that into this inflow formula here, this fraction times 2. In the outflow, you could just put x and simulate this thing. If you simulate this thing, you don't get the fish model anymore. You get this thing that looks ugly like this, where if I try different initial conditions for this system, I get these trajectories that just get more and more different over time. So the different colors here correspond to different initial conditions. And let me zoom in on it to make this clearer. So if I magnify this here, just looking at the early time, then you can see that I've got initial conditions that actually aren't that different. It's hard to see where they start, but there's the kind of a starting point here, there's another one here, there's another one here. So these 3 initial conditions here, and they all start off kind of similar, but over time they get more and more different. And if I go way out in time, then they're not getting any closer together. This is very different than the fish system. And so they maintain their individuality. In principle, I could actually predict what initial condition came if I knew enough about the system just by looking at what trajectory is here. So the identity of the initial condition really matters on the outcome here. I'll talk about the butterfly effect in a moment, or towards the end of this discussion here, but I just want to bring it up here as a reminder to go back to that. It's like, as well mentioned, the butterfly effect, you know, if you've heard about it, a lot of people mistakenly describe it as saying a butterfly flaps its wings in Africa and suddenly it causes a storm in North America. That is not the butterfly effect. I don't know what that is. What the butterfly effect says is in a universe where the wings are down, you'll have a very different outcome of that storm than in a universe where the wings are up. So the initial conditions of the planet matter. And so I have to consider the world. This system here says I cannot abstract away the butterfly. The butterfly's little wings matter because the green line is the universe with the butterfly with its wings up. The red line is the universe with the butterfly's wings down. And so those tiny perturbations in the initial condition of my system are enough to totally change the outcome of my whole system, especially over long periods of time. That's the butterfly effect, which I'll come back to again. And that's what we're seeing here. That's chaos right there. So, so that's the kind of idea here that, does this make sense here? That this looks just like the fish system, kinda. I mean, it's not that different, but it has this weird property that I can have small changes in my initial conditions that, especially over long periods of time, make the outcomes look totally different. Things do not get attracted to a single simple attractor. They get attracted to what we'll call in a second here, a strange attractor, where it's like, it's just weird over time. And it looks random, right? I mean, the behaviors here, they're going all over the place and they don't make any sense. And you might think that, oh, this is just because it's a random outcome, but there is no randomness here. This is all deterministic. It's totally predictable. But the problem is you have to know the initial conditions perfectly. How many people have seen Jurassic Park? Okay. I'm a little surprised because it's kind of an old movie. In another class, actually a different simulation class, I asked about the Matrix. And how many people have seen the original Matrix? Okay, so, and like all of my Matrix references, like, are just like it's just like, no, but like it used to be an awesome pedagogical tool, and now I have to like redo all my slides. But yeah, so Jurassic Park. Does anybody remember when Ian Malcolm, the mathematician, he's kind of flirting with Ellie, and he like drops like water on her hand and says like, look, if it drops here, then it goes this way, and if it drops here, and it's this way. That's chaos, right? So that's what he's trying to communicate in his suave sort of way. Is that the initial conditions, you know, they initially might look very similar, but the outcomes are going to be totally unpredictable, whether it falls off the left side of the hand, the right side of the hand, or whatever. And that's what we're seeing here. So any questions about this general idea of chaos? Questions online? Okay, all right, so what causes chaos? Well, I just showed you one system that displays chaos. And if we sort of think, well, where is it coming from? Well, remember, we talked about if you have a balancing feedback with delay, we talked about how you can get oscillations. So you might expect the system to rise up to its goal and sit there. But if this delay is really high, you get this, what we call an underdamped effect, where the system overshoots and comes back down and goes around here. So you get these changes here. So delay can be a source of oscillations. But in the systems we looked at, the simple systems here, the delay kind of term wasn't that important. It eventually all settled out at the same spot, but the transients looked a lot different. Well, in this type of chaotic system, this Mackey-Glass system, our lesson here is that if the delay is particularly bad with respect to the dynamics of the system, then the system never can quite catch up with itself. And it's kind of like the dynamics of the inflow depend upon a delayed version of then the dynamics of the outflow is a totally different version. So it's kind of like the system is trying to find a balance point, but it keeps kind of chasing its tail. It's like, normally you watch a dog chase its tail, it would just go in a circle. But if the dog was particularly slow at figuring out where its tail was, it might be wandering all over the place. And that's what chaos is. It's a dog trying to catch its tail, but it sort of has so much of a delay in its perception of where its tail is that it keeps going to the wrong place. And in doing so, moving the tail even farther away from itself, so that the initial condition of the dog when it started chasing its tail is going to totally determine whether the dog bounces off this wall or that wall and so on and so forth. That's what we're kind of seeing here. So our lesson here is that feedback with delay can lead to chaos. So whenever you're building a system or analyzing a real world system that has feedback with delay in the feedback loop, red flags should go off. That if that delay is particularly pernicious, bad, then that might lead to an outcome where my real world system might look noisy, but in reality, it's a totally predictable outcome of the system trying to catch up with itself. So that's our lesson. One thing that can lead to chaos is feedback with delay. Okay, so questions about that example? Okay. All right, well, then I want to cover one other thing that can cause chaos. Can we have chaos without delay? Because most of your models, you may not have implemented a delay. And so you'd say, well, as long as I have a model that's sort of fast enough, maybe I don't ever get delay. It turns out that you can get chaos. You can get chaos even without delay, but you need 3 or more stocks. So that'll be the key here, is if you have 3 or more stocks, even without delay, you can get chaos. And it's still actually kind of an interesting, I won't go into a lot of the theoretical details here, but it's kind of like if you were forced to walk on the ground, as we are, and 2 people were bouncing around a room, just reflecting off the walls randomly, kind of like Roombas, vacuuming or whatever, there is a non-zero probability that those 2 people or those 2 vacuum cleaners will hit each other. And so for reasons involving that, if you only have 2 stocks without delay, you can't get chaos. But if those Roombas can fly, so now they're bouncing off the ceiling and the floor and the walls, there's actually, you can show that there's a 0% probability that they'll ever actually hit each other if the Roombas are sort of sufficiently small. And that is a little bit like a dog chasing its tail and not ever being able to catch it. It's like these 2 Roombas will never be able to catch each other if they're just randomly bouncing off the wall. And again, I don't want to go into the theoretical background there, but that is part of the reason why you need 3 stocks to get chaos. So if you have 3 stocks, and here are 3 stocks here, and I just abstractly call them X, Y, and Z, but these could be like population, water, and I don't know, energy resources or something like that. So this could be a model of a city or whatever. Just had 3 stocks in it. And I just have inflows. And I my inflows have this structure, and this is what's called a Lorenz system. Any system with this structure is called a Lorenz system. And there's a bunch of Greek letters, but they're just constants. They're just parameters that are kind of filled in here. And so this actually isn't that complicated looking of a system. So up here, the inflow going into X is just Y minus X times 10. And you can see on so on and so forth here. So for Y, I could have modeled an outflow where, it's just equal to Y, but I just, for simplicity, bundled it all into the inflow. And so my inflow is going to have a minus sign in there. But so this is a system you can build in Vensim, and it's not really that much more complicated than the systems that you're building for your final projects. 3 stocks with interconnections. And this particular system and a bunch of other systems like it exhibit chaos. And what I mean by that is if I simulate this system, and I put a note here that if you try to simulate this at home in your model settings for your simulation in Vensim, you have to change at the very bottom. I never talked about it, but it said like integration method, and it says Euler. And I said, don't worry about that. You, in order to make this simulation work properly, you have to change that to this thing called RK4 Auto, way outside of the scope of this class to understand why. But that's, if you want to try to generate these results at home and you're not getting the results that I get here, it's because of that. So if you've taken a differential equations course, then you can start getting into what this comes from. But so that's what this note is down here. So if you do that and simulate this thing, I can plot a Y behavior over time, an X behavior over time, and a Z behavior over time. And all 3 variables, all 3 stocks, have the same sort of property where I have different initial conditions in each one of them. So I have 3 different initial conditions, and they all start out kind of similar. So all 3 colors overlap. But after some time, they start diverging. So it's like the opposite of the fish model here, where they start close, but then they end up very far away, and they have kind of their own sort of personality. And so I get chaos without even delay here. So the lesson I'm trying to get here is for 3 stocks or more, you can get chaos. And so it's something that you always have to look for because you're never quite sure if it's there. So that's why whenever you run your systems, you should probably try them with slightly different initial conditions to see if you get the same outputs. Because if you get a slightly different output, then if that's the right model, then you really need to get your initial conditions right. Hopefully you don't have chaos in your system, and you don't actually need to get the initial conditions right. You just set them to something plausible, and then you let the system run, and then a steady state is all you really care about. And that steady state will be the same regardless of initial conditions. These systems, that won't be the case. So that's a lesson here. If there's 3 stocks, you get chaos. Now, what if you have a signal that you took from real world data, and you're not sure if it's just random, whatever. I mean, in other words, I haven't included all the variables and the boundaries of my system, or it's chaotic. A beautiful thing about chaotic systems is the behaviors over time look random. So in this picture, if I go back, this picture where I've got time on the x-axis and the stock on the y-axis, this looks kind of ugly and sort of random, like noisy. But if I instead, and there's a way to do this in Vensim, plot one stock versus another stock, like X versus Y. If I do X versus Y, so every point here, this is like at some time instant in the simulation, I grab an X, stock value, and a Y, and I plotted those together. And this is what we call a parametric plot. And so if I plot X versus Y, where time doesn't show up anymore, it's just the relationship versus X and Y, I get this funny little shape that does not look random. And if I choose different initial conditions for my system, I get the same shape. So plotting stocks against each other is a way to detect if this was truly random behavior over time in the previous slide here, if this was truly random, plotting X versus Y would just give me a random relationship. I wouldn't get any structure. But because there is structure, there is an endogenous structure in the system driving this, then if I plot X versus Y, even with the different initial conditions, I get the same pattern. And I can even plot in 3D all 3 stocks, X versus Y versus Z. And that's what this animation is right here. And it's going to rotate. So right now you're seeing X versus Z. And in a second, it's going to rotate, and you'll see, I think, whatever x versus y, or this is z versus y, and then it'll rotate. It'll show you x versus y. And it shows you this funny kind of butterfly-shaped thing. And this is called the Lorenz attractor. And this is a so-called strange attractor. So in the fish system, everything was attracted to carrying capacity. It was a simple point. In chaotic systems, things aren't attracted to a point. They're attracted to shapes. And they just rotate around these shapes until the end of time. And it's slicing these shapes so you only look at x, y, or z individually, makes it look random. But when you zoom out and think of x and y together, then it starts showing structure. This is similar where, like, if you look at things orbiting the sun, if you keep track where the Earth is every time it goes around every year, it doesn't actually go around and hit exactly the same point in space every year. Sometimes it's above that point, sometimes it's below that point, and so on and so forth. And if you only looked at where the Earth was at January 1 at the beginning of every year, in terms of like the kind of like the kind of height in the solar system, then you might think it's totally random. But if you kind of like zoom out and look at the Earth's trajectory, you realize it's kind of like maybe wobbling a little bit, like it has structure. And that's the same idea here. And so these structures, like I said, are called strange attractors. And chaotic systems have these strange attractors where they provide an insight into that there really is, it's totally deterministic what's going on. All right, so any questions about this visualization? So yeah, I think I can show it kind of, yes. So this endogenous pattern only becomes clear when you observe the variables simultaneously. If you observe them one at a time, they look random, whatever random means. Okay, and so I think here, so if you look at a behavior over time and it has apparent randomness, that you really need to look at how variables relate to each other. Because if there's endogenous structure and you plot these variable relationships, you're going to actually see that, oh, whenever x is large, y is small. Whenever x is small, y is large. So by plotting the x's and y's together, apparent randomness in x turns into actually a relationship between x and y. And that's what we're showing here. All right, so any questions about this idea, about strange attractors and this idea of plotting variables against each other instead of against time? That makes sense. Questions online? All right. All right, so this is Lorenz, the same Lorenz over Lorenz here. So his definition of chaos is when the present determines the future, but the approximate present does not approximately determine the future. So the first part of this is present determines the future. That means it's deterministic. There's no randomness. If you know everything exactly now, you know things exactly as there will be in the future. But in chaos, if you don't know things exactly now, that uncertainty from how things actually are actually adds up, so that in the future, things are going to be way different than from your predictions, because you didn't know things. It really matters whether the butterfly's wings are up or down. And that brings us to the butterfly effect. So again, it's not about the butterfly flapping its wings and like getting a little puff of air. That's stupid. Like, I don't know, like that's just a total misinterpretation. Butterflies are not flapping their wings and creating atmospheric disturbances. The idea here is that there's, that if you were to imagine a multiverse, a universe with a butterfly with its wings up might have a very different atmospheric outcome than a universe with a butterfly's wings down. That's really what the chaos effect is. You would imagine, without worrying about chaos, that it's not going to matter if the wings are up or down. You go into one universe or another, and if everything else is the same except for the butterfly wings, you're going to get the same atmospheric patterns everywhere. That's what you would think, because why would it matter? But chaos is saying that something as a tiny detail as getting the position of the wings wrong. Well, so if I assumed I'm in a universe where the butterflies have the wings up and actually the wings are down, then my simulation model will give me totally different weather patterns than the weather patterns that actually exist. That's the butterfly effect. It's not about the causal relationship between the butterfly and the weather. It's about sort of the nonlinear relationship between about the butterfly and the whole system. It's about getting the initial conditions right. Does that make sense? Now, in reality, most of the people outside this classroom are going to use the butterfly effect for rhetorical purposes that, so, I mean, you can use the butterfly effect however you want, because, most people don't really care about whether they're getting it right in the mathematical sense. But at least in the terms of dynamical systems, when you talk about the butterfly effect, this is what you're talking about. Okay. All right, so questions about chaos and the difference between chaos and randomness. Questions online? Again, the big things I want you to remember about chaos, you don't need to know about the formulas for the Lorenz attractor, the Lorenz system. But what I do want you to know is it's an extreme sensitivity to initial conditions that gives the appearance of randomness when there's actually totally endogenous structure. So randomness is an exogenous thing. You don't know what's causing it. It's just random. It just happens. Sometimes the outcome's a 1, sometimes it's a 6, and we can't predict it. So randomness is sort of exogenous, whereas chaos, there's no exogenous factors. It's all inside the system, and yet a simple system produces very complex outputs. All right, so with that, what do we got ahead of us? We have an open lab on Tuesday, so keep working on your projects. Muddiest point coming up, no more homeworks or anything like that. So the open lab, if you don't, if you think you're good, you don't have to come on Tuesday. I'm not gonna be taking attendance or anything like that, but we're here to help. So, and likewise, I'll be online to help. You can send emails, you can set up times for office hours, whatever. Then on Thursday, Eric will give a lecture that, and this is not something to blow off, because I will be watching his lecture myself and be taking down questions that I will introduce at least one on the final exam from Eric's statement or comments there. And it will be a sort of real world application of how to use quantitative methods that involve thinking about dynamics and causation and stats and such like that. So, and then in our last week of class, like I said, Tuesday, final exam review. It's just going to be, I'll bring slides that are kind of the greatest hits, but you could just bring questions. We could fill it with questions. We could work problems. There's a bunch of sample final exams that are online that you can access. You might have to do that that lockdown browser test for the final exam to get access to them. I think I have a sample online exam that you can take as many times as you want. Then Wednesday, that's when your final presentation and reports are due, and it really is 11:59, so you got to get them in by that night. That way it'll be able to randomly generate the assignments for the peer reviews. Peer reviews will then be due Saturday, right before finals week. And then our first stage 1, which is lockdown browser, will be Thursday. And like I said, I'll open it up so you can take it anytime Thursday, anytime Friday, anytime Saturday. You'll get a 90-minute window, just like the midterm. If you want to come here for that 90-minute window, that's fine. And I can sort of proctor it for you, but you'll still have to use the lockdown or whatever. But you don't have to. You can take it wherever you want, as long as you can use the lockdown with the camera. And then during finals week, stage 2 will be that, and it's collaborative as in a midterm. So open book, open notes, open Canvas, open students who are currently enrolled, but not open Chegg, open Course Hero, or anything like that. So no internet resources, just Canvas, your notes, the book, etc., and the students currently enrolled. All right, so any questions moving forward? Everything pretty clear? All right, so let's finish with the last attendance exercise here. And the question is, chaos is extreme sensitivity to what? So chaos is not randomness. Chaos is an extreme sensitivity to what? So fill in the what. And that's all I've got for you today. So if you have any questions, feel free to come up. Otherwise, we'll see you next week. Have a good weekend. Don't forget about your muddiest points. Well, I'm gonna stop the recording for this, but I would say, I mean, I don't like.